we are now going to define another vector operation called cross product. This is the only vector operation that is specific to dimension. Cross product only exists in 3 dimensions and it can't be used in any other context. It's a major physics application. So the concept of cross product is fairly simple. I have 2 vectors in space. They are not multiples of each other, and these 2 vectors uniquely determine a plane. They can only live on one plane simultaneously. What the cross product is designed to do is come up with a vector that is orthogonal or perpendicular to that plane, and then it can describe that plane. So what we want to find is we want to find a vector W. Let's call it W1, W2, W3, so that U dot W equals V dot W equals 0. I want to find a vector that is simultaneously orthogonal to both U and V. And so the way I'm going to do that is I'm actually going to perform the dot product and carry it through. So I want U1 W1 plus U2 W2 plus U3 W3 to equal 0, and simultaneously V1 W1 plus V2 W2 plus V3 W3 to equal 0, and then solve that system of equations. Now, I'm not going to do that for you here. It takes actually quite a bit, and if you haven't had linear algebra, the matrix algebra might blow you away a little bit. But if we solve that system of equations, we come up with the results that W1 equals U2 V3 minus U3 V2, W2 equals U3 V1 minus U1 V3, and W3 equals U1 V2 minus U2 V1. So we're going to put these together next. So now putting it into vector form, this is the result that we're looking for. This is the vector that should be simultaneously orthogonal to both U and V. And we define this to be U cross V. Now, if you notice, if I do V cross U, then all of my subtractions would be in the opposite order. And so therefore, we see that cross product is not commutative. That's one of the interesting things. So which way this vector points is very interesting. So most of you who have seen this before, you learned something called the right-hand rule. So if I have my fingers pointing in the direction of U, and let's say V is that way, and I go towards V, my thumb's going to go this way, which means that the cross product would be pointing upwards. But if I went from V to U, I can't bend my fingers backwards, so I turn my hand over and go this way, and now the cross product would point in exactly the opposite direction. So cross product is not commutative, but I would get the same numerical values. Now, to do a quick check, I would like to do U dotted with U cross V, and see what we get. So if U is U1, U2, U3, then this result would be U1 times U2 V3 minus U3 V2 plus U2 times U3 V1 minus U1 V3 plus U3 times U1 V2 minus U2 V1. If I distribute here, U1, U2, V3, U1, U3, V2 plus U2, U3, V1 minus U1, U2, V3, and then finally plus U1, U3, V2 minus U2, U3, V1. So doing a quick check, you notice that this term here cancels with this term here. This term here cancels with this term here. This term here, and I get 0, which was the desired result. So we've just proved that U is orthogonal to the cross product. If we do the same thing for V, we'll see that V is also orthogonal to the cross product, which accomplished our goal. Most of the time I've found when people do cross product, they make it far more complicated than it needs to be, and then they still end up getting incorrect results anyway. So I'm going to do a very simple example. Let's say this is vector U and this is vector V. So think of this as your U1, U2, U3, V1, V2, V3. Rather than memorize a formula or do some crazy antics, the formula says U2 V3 minus U3 V2. So I just need to go -5 minus 6. The next term is u3v1 minus u1v3. So 12 minus 10. And then the last term is u1v2 minus u2v1. So negative 4 minus 4, that's negative 8. That's it. If you're doing more work than that, you're making it too difficult. Now, it's always possible I made an arithmetic error, so you should always check your cross product by doing a dot product. It doesn't matter which vector you choose. You're either going to get 0 in both cases or 0 in neither case. So let's suppose I choose the first vector. When I do this dot product here, I'll get 22 plus 2 minus 24, which is 0, and there's my check. I did it correctly. Now let's consider the one odd case where I take two vectors that are actually multiples of each other. That means they are on the same line. That means they do not uniquely determine a plane. So let's see what the cross product looks like in this case. So doing the same thing we did before, this product minus this product would be k u2 u3 minus k u2 u3, 0. k u1 u3 minus k u1 u3, And then finally, k u1 u2 minus k u1 u2, we get the three-dimensional zero vector. This should not surprise us because remember, the zero vector is automatically orthogonal to all vectors because the zero vector dotted with any other vector will always produce the number 0. So obviously, it's going to produce 0 in this case, but also the zero vector is orthogonal to whatever plane these live on, and these live on infinitely many planes. So this is the one odd example, but it still works. Now, check Canvas for the posted notes. I've gone in great detail to derive lengths and several examples. So if you put the two together, hopefully you have a complete picture of cross product.